Hi, my name is David Kramer-Bang, and I would like to present our newest paper called Rates of Convergence for Multivariate SDEs Driven by Levy Processes in the Small-Time Stable Domain of Attraction. This paper is in collaboration with Jorge González Cáceres from EMAS UNAM, and I'm from the Department of Mathematics at Aarhus University. So, the setting in this paper is that we consider a multivariate Levy process on Rd(x) and an alpha stable process on Rd(z) with alpha between 0 and 2, and that we say x is in the domain of attraction of z, meaning that if we look at the correctly scaled process x of st divided by g of t, this converges in distribution to z of s as t tends to 0 because we're looking in the small time stable domain of attraction. In this case, our scaling function small g is given by t to 1 over alpha times a slowly varying function capital G. We'll split in two different cases. So we'll say that x is in the domain of normal attraction if g converges to a positive finite constant as u tends to 0, and otherwise we'll say that x is in the non-normal domain of attraction. And we'll use this notation throughout the paper for the rescaled process. So many Levy drivers lie in the small time domain of attraction of some alpha stable process Z, and this gives us a chance to do stable approximation at high frequencies. For example, a big class of these processes is tempered stable processes, which exactly leads to domain of attraction. So for us, the goal is to quantify the rates at which the solutions to the SDEs driven by xt and z converge to each other. And the general theory behind this is based on two couplings called the thinning coupling and the combinatonic coupling, which we'll come back to later. So our SDE setting is given as follows. We have some Lipschitz continuous function v with some appropriate function k, such that it satisfies this inequality, and for some appropriate Euclidean norm. Then we consider the solutions to the SDEs curly z and curly xt, where the SDEs are given by this nonlinear form. Okay, and again, xt, which drives the curly xt, is given like this, which is in the domain of attraction of z, which drives the curly z. For alpha between 0 and 2, excluding 1. And now the goal is to quantify the rate at which xt, so the solutions to this SDE, converges to curly z. So the underlying couplings is split in two. So we have the thinning coupling and the combinatonic coupling, which are fundamentally different. So the first coupling, the thinning coupling, builds on constructing a dominating Levy measure which dominates both the Levy measure of xt and z, and using this dominating Levy measure to construct a common Poisson measure, and using this to construct the compound Poisson processes for x and y, so x and z. And by constructing this and thinning a common Poisson measure leads us to sharing as many jumps as possible. So as you see in this simulation here, where you have a circle and a plus, they share both the direction and the magnitude of the jump, so they share the jump exactly. And where you have either a circle or just a plus, they don't share anything, so they have vastly different directions and magnitudes. So under this thinning, we have that many of them, as many as possible, are exactly the same, whereas the rest we will aggregate some kind of error from the non-matching jumps. Now for the combinatonic coupling, we do a different thing. So we construct a shared angular measure, so they will always jump in the same direction, and then we'll couple the magnitudes of the jumps in a combinatonic way. Okay, so that means that we start constructing a angular measure so that they always jump in the same direction, as we can see in this simulation down here. And then we optimally couple the magnitudes of the jumps. So we'll always have some kind of small error, but then we will aggregate this error in the magnitude instead. And it turns out heuristically that aligning the directions and then combinatonically coupling the magnitudes yields better rates than sharing as many jumps as possible, and then just trying to handle the aggregation of the leftover errors. Okay. So some of these couplings were used in a paper where we consider the rate of convergence for the drivers themselves. So what is the rate at which the driver xt converges to Z? And this was done in collaboration with Jorge González Cáceres and Alexander Mijatovic. And here is a small overview of the results. And here we see that we get polynomial rates for domain of normal attraction, and we get slowly varying rates for domain of non-normal attraction. And we even get lower bounds for alpha between 1 and 2. Okay. So what about the SDE setting? So this is of course an extension, and I'll start by presenting our results for the case of augmented alpha stable drivers. So we'll say that the Levy process is an augmented alpha stable process if it has no Gaussian component and if its Levy measure has this radial decomposition for alpha between 0 and 2. Specifically, we have some probability measure sigma, which is our radial component, and then we have some q, which is some measurable slowly varying function. If this q is a constant, appropriate constant C alpha, then this is exactly the definition of being alpha stable. So this class of augmented alpha stable processes includes a lot of examples. So it has a big subclass of the Rosinski's tempered stable processes, some truncated stable processes, beta class of Levy processes, and some metamorphic Levy processes. So this is a large class of Levy processes, which are in the domain of attraction of an alpha stable process. So this is the corollary. So we say that if X is an augmented alpha stable process, which is in the domain of attraction of an alpha stable process Z, then there exists a coupling between xt and Z for which our solutions make this family tight. So this family is f of t to the minus 1, the supremum norm of xt minus Z, and it's tight for some specific f and g. So the g is the scaling function of x, and the f is this scaling function here. Okay, so if we have some assumption which quantify the similarities between the Levy measures of our augmented alpha stable process and our limiting alpha stable process given here, then our small g function is just t to 1 over alpha, and our f function, which makes our family tight, is polynomial. Okay, so the power of the polynomial is different, and that varies from if we have infinite variation and if some balancing condition fails, which is given here, or if we have the balancing condition holds, or we have for all alpha between 0 and 1. In this case, where alpha is between 1 and 2, and the balancing condition holds, or alpha is between 0 and 1, we can see that we can get arbitrarily fast rates, because you can find, if you can find some assumptions where this p holds for larger p, then this can become arbitrarily fast. Now, what happens if we instead have some assumption on q, again, which quantify the similarities between the Levy measures, but it's more general now. It's C alpha times capital H of x for some monotone slowly varying C1 function h. Well, then we have our two different couplings, which leads to two different rates. So first of all, if our h is of controlled slow variation, this doesn't have any positive limit at infinity. h2 is slowly varying, and t times h of t to minus 1 of alpha is increasing with some appropriate inverse function, which has g to be slowly varying. Well, then our scaling function making xt converge to Z is t to 1 over alpha times g of t, and our f, which makes the family tight, is slowly varying. It's specifically h2 of g of t to 1 over the ceiling of alpha. So the biggest difference here is that we now have a slowly varying rate. Again, constructing a row from the h and looking at the inverse, the right continuous inverse, row right left arrow, we can see if this G constructed H of row inverse of 1 over x is slow because of control slow variation for some slowly varying function G2, then again we have the same small g of t, and our function f is again slowly varying. So it really does heavily depend on if you're in the domain of non-normal attraction or if you're in the domain of normal attraction. So the class of control slow variation we'll get back to, but roughly speaking, it just quantifies the rate at which L of xt divided by L of t converges to 1. Right? And this has to converge to 1 since L is slowly varying, but it just gives us a control over this rate. Okay. So in more generality, if we have some assumption t, which decomposes the Levy measure of x into some finite mass Levy measure and some Levy measure nu x c, which again quantifies the similarities between the Levy measure x and the limiting Levy measure nu z. The assumption is given here. Under this assumption, then we know that the family is tight. Specifically in the domain of normal attraction, our capital H will be 1, making both G and H1 equal to 1 and H2 0. The scaling function is just a polynomial t to 1 over alpha, and our rate is polynomial. Again, we have the case that we have one rate if we have infinite variation and the balancing fails, and if the balancing holds, or if alpha is between 0 and 1, we have a rate which can be arbitrarily fast. And of course, this depends on alpha. So if instead we're in the domain of non-normal attraction and H is of controlled slow variation, where H2 is slowly varying, then our rate F is now slowly varying. So similarly for our combinatonic coupling, we have a main result. Again, this depends on our underlying radial form, which depends on some common radial probability measure sigma and some family of Levy measures rho x c, which again are quite technical, but they're given here, and they quantify how similar the Levy measure of x is to the limiting Levy measure of z. And again, we need inequalities like these to control these differences. Okay. And they are controlled by p and delta. So for the combinatonic coupling, our family f of t to the minus 1 times the supreme norm is tight. In the domain of normal attraction, again, h being equal to 1 gives us that both g and g1 are 1, g2 is 0, and our scaling function g is just t to 1 over alpha. Now, if p is not equal to alpha minus 1, then we just have this polynomial rate here. And of course, alpha between 1 and 2 and our balancing, some appropriate balancing condition fails. If the balancing condition holds, or alpha is between 0 and 1, then we have t to the p over alpha, again, which can be arbitrarily fast if we can choose p as large as we want. Under the domain of non-normal attraction, we have h of controlled slow variation, g of controlled slow variation, g2 is slowly varying. Then our scaling function is just t to 1 over alpha times g of t, and the function f is equal to g2 of t, which is slowly varying. So again, we go from having a polynomial rate which can be arbitrarily fast to having a slowly varying rate which can be arbitrarily slow. This could be iterated logarithms, so this could be arbitrarily slow. Okay. So what causes this slow convergence? So to know a bit more about that, we'll go back to this definition of controlled slow variation, which is given here in full. So we say that L is of controlled slow variation if it's slowly varying, with controlling functions phi1, which is slowly varying at 0, slowly varying at infinity, and locally L1. And we can find some phi2, which goes to 0 as t tends to 0. And L is just equal to 1 for all large t, and then the rate at which this fraction converges to 1 is controlled by phi 1 and phi 2. Then Burgers and Greengard proved that if L tends to either 0 or infinity, then phi 2 cannot be faster than any power of logarithm, meaning that this rate has to be slow. And this will come up in the rate when you calculate bounds that quantify tightness. So you cannot get around this type of bound, which really has to be slow due to this principle. Good. So some illustrations of tightness is that if we consider various t's, then for any of these t's as r tends to infinity, this probability here has to tend to 0. Okay, so we have plotted some cases here. In this case, we have the tail probabilities of the rescale pathwise difference between these couplings of these SDEs, these nonlinear SDEs. And in this case, it's in R2. We have alpha is equal to 0.7, and V is just the rotation matrix that rotates with the angle norm of x. Okay, and you can see here clearly all of them converges to 0. Okay, so a clear difference is that the couplings lead to different rates. So which coupling is faster? Well, as we sort of mentioned when introducing the couplings in the heuristics, is that the common-tonic case where we construct a joint angular measure and then common-tonically couple the magnitudes lead to better rates. So when alpha is larger than 1, we can see that the rate is improved by up to a factor of 2 versus the thinning coupling, if the balancing condition holds or if the balancing fails and very small p. So this happens since accumulating small magnitude errors but perfectly aligning the direction really helps the nonlinear SDEs more than sharing as many jumps as possible and then controlling the aggregation of the leftover errors. So another thing is that in the SDE case where we looked at the difference between the drivers, we could construct a lower bound for the uniform distance for convergence probability. But this is not possible in this case. And despite these couplings containing optimal Wasserstein rates for the drivers, it's unclear if better couplings exists. Okay. So in summary, when we have these nonlinear SDEs, our scaling function is polynomial when we're in the domain of normal attraction under both the thinning and the common-tonic case, but we can see that up to a factor of 2, the common-tonic coupling can be better. Under the domain of non-normal attraction and thinning or common-tonic coupling, we see that the rate becomes slowly varying. It can become arbitrarily slow due to G2 and H. And in this case, here and in here, you can have arbitrarily fast rates. Okay, so things are very different when we look at additive SDEs. So if we look at additive SDEs, we can use the bounds directly from the Wasserstein distance between the drivers. They can be transferred directly onto the Wasserstein distance between the SDEs. So here we have the SDEs with additive noise. We assume that xt is now a pure jump-Levy process that's in the domain of attraction of Z. Then we have a corollary saying that under some integrability assumption, you can directly bound the Wasserstein distance between the solutions to the SDEs by the Wasserstein distance between the drivers. And I'll again cite this original paper which exactly controls this rate between the drivers. And I'll also cite this YouTube video on the first paper, which really gives a lot of intuition into the general coupling, but also into the fact that you have these slowly varying rates, which can become arbitrarily slow, and exactly what these can look like. There's a very good section on this in the YouTube video. Okay. So what does the proof rely on? Well, first of all, they rely on the couplings, but once you have constructed the couplings, you can use these to construct some general non-asymptotic LP bounds. So if you take two general Levy processes y1 and y2, and you have the solutions curly y1 and y2 for these nonlinear SDEs, then you can construct some general LP bounds in terms of the driver characteristics using the Burkholder-Davis-Gundy-Novikov and a Grünwald application. For these general bounds, when p is equal to 2, we require that both processes y1 and y2 have finite second moment, and when p is equal to 1, we require both processes to have finite first moment and finite variation. So we'll come back to this, but this gives us a problem in applying it directly to our case, because we have Z being alpha stable and xt being in the domain of attraction of alpha stable, meaning that for alpha between 1 and 2, not excluding 2, the processes will not have finite second moment. So we need an additional step, which is our second step in the proof strategy. So here we have exponential change of measure. So we construct some exponential change of measure, which is completely independent of t, which grant us as many moments of any orders we would like. And then we estimate this, the new bound in the characteristics in t. Okay, and then we can use this exponential change of measure to go back, because we have some LP control under equivalent measures, and that gives us exactly the tightness under our original P. So some general takeaways are that we can use these general coupling-based bounds to imply uniform convergence rates and probability for our Levy-driven SDEs in small times. For domain of normal attraction, we have polynomial rates driven by P and some balancing condition, where the combinatoric coupling often can lead to sharper rates in the thinning case up to a factor of 2. In the domain of non-normal attraction, the rates are dictated by the slow variation controllers H2 and G2, and they can be arbitrarily slow, so iterated logarithms. For additive SDEs, so outside of the nonlinear SDEs, we see that the Wasserstein Q rates are directly transferred from the Wasserstein Q rates of the drivers. So final comments are given here. So a most remarkable fact that we found in the paper is that the convergence and probability guarantees that works in this paper can outspeed the lower bounds that we developed for the Wasserstein 1 distance between the drivers. This means that for the upper bounds, in our case here, can be much faster than what we found in the lower bounds. This implies that the family, which is tight, is far from uniformly integrable. So general Wasserstein upper bounds for the SDEs other than additive SDEs is, at least in this case of domain of attraction, are completely infeasible. And why is that? Well, we found some things that worked against each other. So no alpha stable process has finite variance, and all processes with finite mean have infinite variation, and vice versa. Okay, so this makes our general Wasserstein bounds inapplicable. However, more generally, any alpha stable process has either finite beta variation or finite beta moment, and never both. So this really conflicts almost any attempt to use Grünwald's inequality or generalizations of Grünwald's inequality. So if you take fractional powers of Grünwald, which can come up and attempting to apply this in our bounds, and this really becomes completely ineffective. And the reason for that is that the ODEs of fractional power have no uniqueness of solutions. So this ODE given here, which has a fractional power, has no other solutions than 0. So all of these things really become a big problem and makes it completely infeasible to get general Wasserstein bounds for the SDE case. And here are the citations given throughout the paper, and thank you for listening.